Have you ever been talking to an AI like ChatGPT and just wondered, how does it do that? How does it seem to learn a brand new skill right there in the middle of a conversation? It really does feel like magic. But today, we're going to pull back the curtain. We're about to dive into this really groundbreaking idea that you can actually program an AI's behavior, not by rewriting its code, but just by talking to it in the right way.
So here's the big puzzle, right? You ask an AI to summarize a long article and poof, it does it. Then your very next prompt is, now write that summary in the style of Shakespeare, and it does that too, instantly. It hasn't been retrained, there was no update between your questions. So what is going on? How can one single model switch gears like that on a dime? Well, this incredible ability is called in-context learning, and researchers are just now starting to figure out the really elegant mechanism behind it.
And to really get your head around just how radical this is, we need to look at the huge shift that's happened in AI. It's basically a tale of two completely different philosophies for teaching a machine a new trick.
Yeah, this comparison table really tells the whole story. The old way, that was all about task-specific training. If you wanted an AI to translate French, you had to train a model just for that. If you wanted it to analyze sentiment, well, that's another model, or at the very least, a really slow and expensive retraining process. You see, the model's internal parameters, its weights, were always being changed. But now, with in-context learning, the model adapts on the fly, just based on the prompt you give it. Its core programming, those weights, are totally frozen. They don't change one bit. And all of a sudden, you have one model that can do hundreds, even thousands of different jobs. And this all boils down to what we call in-context learning, or ICL for short. It's the model's amazing ability to figure out exactly what you want it to do just by looking at the examples and instructions you put in the prompt. And here's the kicker. It does all this without any changes to its internal parameters. The AI isn't really learning a new skill in the way we think about it, it's emulating it, using the vast knowledge it already has packed inside.
So, this brings us to the absolute core of the research we're looking at today. Because if the model's brain isn't changing, but its behavior is, then something pretty incredible must be happening inside the prompt itself, right?
To make this idea of frozen weights really click, think about a simple calculator. Its internal circuits, its hardware are totally fixed. It's built to do addition, subtraction, multiplication. You don't have to rewire the calculator to switch from adding to multiplying, you press different buttons. Well, this research is suggesting that these huge AI models work in a really similar way. And the prompt, that's you pressing the buttons.
And this leads to the paper's absolutely stunning central claim, something they actually proved theoretically. You can take a basic transformer model, the same architecture behind things like GPT, completely freeze its weights so nothing inside can change, and you can get it to run all sorts of different, complex algorithms just by feeding it the right prompt. The prompt isn't just a request anymore. The prompt is the software.
Okay, so how on earth does that actually work? How can a string of text reconfigure a machine's entire computation without touching its hardware, so to speak? Let's unpack the mechanism because it's brilliant. So it turns out a really well-designed prompt does way more than just tell the AI what to do. It can actually encode the specific mathematical parameters of a whole algorithm into the text itself. It's almost like you're secretly embedding a new piece of software directly into the model's import.
Okay, so here's a breakdown of how it works. First, the algorithm's parameters get encoded into the prompt's tokens. Think of it like hiding a secret formula inside a sentence. Now, this special encoding creates such a strong signal that it literally forces the model's attention mechanism down a very specific path. It has no choice but to follow. And by guiding the attention just so, the prompt makes the model execute the exact computational steps of that algorithm. And finally, it spits out the correct answer with incredible precision.
Here's a really great way to think about it. Imagine you have a recipe, but the ingredient list itself is also the entire instruction manual. The specific way you list flour, then sugar, then eggs doesn't just tell the chef what to use, but it also dictates the exact order and method for mixing and baking. That's the prompt. It's the what and the how, all bundled into one elegant package.
Now, this isn't just some cool theory on a whiteboard. The researchers actually put this to the test. They proved that a single frozen model could act like an entire library of different powerful algorithms. So let's check out the results. And just look at this list. We're not talking about simple stuff. These successfully prompted one frozen model to emulate one-step gradient descent, linear regression, ridge regression, and lasso regression. I mean, these are all fundamental algorithms in statistics and machine learning. To get one model to execute all of them just by changing the input text, that's truly remarkable.
And the performance? I mean, this is just staggering. This table compares a baseline model, one that was specifically and painstakingly trained for each individual task, against their single prompt program model. And for lasso and linear regression, the results are just wild. The single frozen model that was just given a prompt actually performed better. It had a lower error rate than the specialized models. This just goes to show how incredibly powerful and efficient this approach can be.
And that really brings us to the researchers' core conclusion, which is just so profound. They say that these massive pre-trained models are essentially universal libraries of algorithms. We don't need to build a new tool for every single problem anymore. We just need to get better at checking out the right book from the library using a well-crafted prompt.
You know, a discovery like this forces us to completely reevaluate what a prompt even is and what it's capable of. It opens up this absolutely fascinating question about the future of how we interact with and maybe even build all technology.
Ultimately, what this all means is that we have to stop thinking of prompts as just simple questions or requests. We need to start seeing them for what they really are. They're callable subroutines. In programming, a subroutine is just a self-contained set of instructions that you can call anytime you need to perform a specific task. And that's exactly what these prompts are doing, calling up a specific algorithm from the AI's vast internal library.
And so, that leaves us with this final, powerful question. If you can execute complex mathematical algorithms just by writing the right sequence of words, are we on the verge of a completely new kind of programming? A future where the most powerful coders aren't just fluent in Python or C++, but are masters of natural language, capable of programming the most complex machines we've ever built, simply by talking to them. What does that future look like?